Actually, the reason I started this lecture was I was at a course in the Netherlands 20 years ago, and I said to the students, do you know when fluorescence was first observed? And they thought about it, they said they think in the 1940s by this guy, Tay Forster. And no, it goes back a little older than that. So I think it's interesting to see why. But first of all, I have to say, oh, I have to learn how to use this thing. Happy Thanksgiving yesterday. I know you don't care, but my girlfriend Sandy bought some empanadas and we had them in the room. So we had empanadas for Thanksgiving. So unfortunately, not unfortunately, but since this thing is locked into Thanksgiving, I realize I'll never have Thanksgiving again, the normal one, but that's all right. It's worth it. So where do I point this to get this to work? Oh, at this. So discovery and characterization. It was actually Nicholas Monardis in 1565. He was a Spanish physician. He never went to the New World, but he read the notes of the conquistadors that went, and he's credited with describing this wood, which they would take this wood from a tree and make it into cups, and they would see this blue tinge. And it was actually, boy, I think I better use this. This is too sensitive. But it was actually Bernardino de Sahagún, a Franciscan missionary, that went to the New World, and he described the wood which was called Caotli by the Aztecs. So the Aztecs talked about this, and they would make this cup of this wood, and it was good for the kidney, basically. People have kidney problems. And Ulysses Acuna gave me this. My friend in Spain, who was a fluorescence guy, went and read the original work of Monardis and all these people. And it was this Flemish botanist, Charles de Lecluse, that gave the name lignum nephriticum, or kidney wood. And it was very popular in the 16 and 1700s in Europe for its medicinal values. In fact, even today, you still can buy this wood, and you'll see Leonel has some from Mexico for medicinal things. And Robert Boyle of the gas law Boyle was inspired by this too, and he investigated it very fully. And he discovered that after a while, you kept filling it with water and throwing it out, it lost the power to give this color, and he concluded there was some essential salt in the wood responsible, which was very clever. But he also discovered that when you add acid, the color vanished, and when you add alkali, it came back. And this is what he actually was. My friend Katie Reinhardt gave me the original manuscript, a copy, and he said when he added a little spirit of vinegar, then this colorless or blue color immediately vanished. But when he added a few drops of oil of tartar del deliquium, and it took me many hours to discover that's potassium carbonate in the old way time, it would come back. So he used it, he was the first to use it as the pH indicator, and he did. In his experiments, he would use the lignum nephriticum to say if things were more acid or more alkaline. And you can look at his other papers, and he's actually using this as so he's using fluorescence as a pH indicator in the 1600s. So the identification only came with Ulysses Acuna and his group, and it's this rearrangement in alkali that goes to this fluorescent molecule. It's got a quantum unit of 1, so it's very bright. And that's it. And this was a picture when I first in my lab dropped some in alkaline with a hand lamp. You could see this light up. Did you want to try this? Here, so my lovely assistant will now attempt to do this. I take no responsibility unless it works. It We probably have too much light from around the room, but we'll see. It's very hard to find a good, lovely assistant now.
Just nice having solution. This is the new critical that compress from Mexico is made.
Can you stir them around? Oh, there. It works. I applaud my lovely assistant. But really, it was when I first saw it, it was just remarkable. I just jumped in the lab. And actually, very recently, there's been some other papers in the literature. This is 2018 with other fluorescent woods. This is from the sycamore tree, and it's a different molecule, scopolamine. So these things do occur in nature, but it was actually described by the Aztecs in the 1500s. So we go back a little ways. And although this isn't about fluorescence now, but phosphorescence, Galileo described the emission of light, which from the famous Bologna stone. And the Bologna stone was a stone discovered by this guy, a Bologna shoemaker, in 1603. And he discovered that if he had this stone in the sunlight and then brought it back into his house at night in the dark, it would give off light. But what was great was what Galileo said about this. And this next statement, I went with Enrico Grattone to the library in Illinois, and he found the original work and translated. And Galileo wrote, "It must be explained how it happens that the light is conceived into the stone and is given back after some time as in childbirth." So Galileo recognized somehow you're getting this energy into the stone, and later it comes out, which was anticipating the whole concept of the fluorescent lifetime. And again, in 1603. So as you see, this didn't happen. This all was thought out many years ago. Now, in 1833, David Brewster described that if you shine a beam of white light through an alcohol solution of leaves, you would see a red beam. And of course, that's chlorophyll fluorescence. And chlorophyll fluorescence is very important now, and they take little fluorometers out into the field and look at the fluorescence. But we also take it out of this world because now they have satellites that go around and shine lasers and look where, look, here you can see in Brazil and in Africa, where you have so much vegetation, and they monitor that from satellites with the chlorophyll fluorescence. So it's remarkable how far this is progressed. Now, the work of Herschel, I think, is extremely important for fluorescence. And John Herschel was a mathematician, astronomer, chemist, experimental photographer, and inventor. He named 7 moons of Saturn and 4 of Uranus, which was discovered by his father, Sir William Herschel. And this is a photograph he took of himself in 1867, which is remarkable, these amateur photographers. And he also translated the Iliad of Homer and invented blueprints. So this guy did a lot, you know. But in 1845, he made this extremely important observation for all of us, the first observation of fluorescence from quinine sulfate. And he termed this phenomenon epipolyc dispersion. And this is actually from his paper on the case of a superficial color presented by a homogeneous liquid internally colorless, 1845. And he described it as an extremely vivid and beautiful celestial blue color. And I like the way they wrote. These guys back then wrote so beautifully about, instead of saying, well, it emitted at 450 nanometers, this is a nicer way to say it. And now I say, this is quinine. Is this perhaps the most important molecule in the development of the fluorescence field? Well, you can judge. As you know, quinine is a bitter compound, comes from the bark of the cinchona tree. Okay, the tree is commonly found in South America, Central, Caribbean parts of Africa. This was the only source of quinine, and already the Spanish conquistadors learned that the locals used this as a cure for malaria. So in the 1600s, it started going back to Spain from the colonies, and it made its way to the Vatican, and that was it. It was very important. For more than 300 years, these trees were the only source of quinine. And as we'll see, the efforts to synthesize quinine ultimately led to the development of the dye industry and commercial fluorescent probes, okay? And here's a gin and tonic. If you, I mean, of course, I've heard that bars had UV lights, but it's the quinine water. And if you go to a bar and they have UV lights, you can actually see the quinine fluorescence. And it is a beautiful color. All right, I drank this afterwards, but the most important paper, I think, came from George Gabriel Stokes. And of all the people, he has to be considered the father of fluorescence. Okay, and this is his paper, which I have a PDF. If anybody wants it, you could email me, I'll send it. But he talked about this paper by Herschel, and again, he discussed the beautiful celestial blue color. And he wrote this massive paper, 100 pages. It's a spectacular paper. When I first got it, I just read it straight through. But in this work, he initially used the term dispersive reflection to describe the phenomena, because that's what people called it. People like Newton thought it was a reflection or refraction of light. But then he put a footnote at the bottom of one page, and this is it. He said, "I confess I do not like this term. I'm almost inclined to coin a word and call the appearance fluorescence from fluorspar, the mineral, as the analogous term opalescence is derived from a mineral." If not for him, you would be attending the 5th workshop on dispersive reflection. So think of that, how much he realized there was something being light absorbed and emitted. And in his paper, he even speculated that maybe there's a time and he could maybe build a rotating mirror and measure this, which would have been very difficult back then. But he derived in this paper the Beer-Lambert law, but he never published it except for this. But it's remarkable, this paper. He also used to go out, he had sunlight, but he'd hold it up to lightning on a stormy day and see if the lightning would do it any differently. So it was remarkable what he did. And the other most important thing he did was this. He used a prism to disperse the solar spectrum, illuminated a solution of quinine. He saw there was no effect until it was placed in the ultraviolet region. So when he couldn't see it, and he wrote this beautiful, beautiful sentence. It was a curious sight to see the tube instantaneously lighted up when plunged into the invisible rays. It was literally darkness visible. Altogether, the phenomena had something of an unearthly appearance. And this led him to proclaim the fluorescence as longer wavelength and exciting. So that's where we got the name Stokes shift, from that sentence there. But the next important thing came from William Henry Perkin, okay, who was the man who synthesized mauve, and here's the color. It was from the flower, which was mauveine, the flower. And here's a picture. He was an amateur photographer too, and he took these pictures of himself at 14. But at the age of 18, he was working for a chemist, and he set out to make quinine again, because they needed quinine for the British troops who were all over the world in malaria regions. And he oxidized coal tar and basically oxidized allyl-toluidine, and he accidentally produced mauve. Fortunately for him, Queen Victoria loved it. He realized you could dye cloth with this. And this was the gown she wore at her daughter's wedding, which was the first gown made of mauve. So he started a company to produce dyes, and they say he produced green and violet, and they say the canal outside his factory turned a different color every week. This was before we had the environmental protection agencies. Others synthesized dyes, but Perkin was the guy that realized the potential for commercialization. He started the synthetic dye industry. Histologists started to use these dyes to stain samples within a decade. And this all finally moved to Germany, but it all started with Perkin. And it was Adolf von Baeyer in 1871, a chemist that synthesized this compound. And I don't have to tell you what that is. Maybe I do. Fluorescence in 1871. To this day, the most commonly used fluorophore ever. And that's his paper. And I started to wonder years ago, why did he name it fluorescence? And he said, well, it's fluorescence. No, it was FLUO from fluorescence, but racine, which was the German with resorcinol, which is what he reacted with phthalic anhydride. So the name tells you how he synthesized it. So that's why it's fluorescence. And he got a Nobel Prize in 1905 for all of his work in chemistry. One of the first experiments, well, probably it went around the party circuit with everybody having fun, but in 1877, adopted this wonderful groundwater tracing experiment where he took 10 kilograms of fluorescein and added it to the Danube. And he even says on Tuesday, October 9th at 4 o'clock in the evening. And then he saw the effect of the same in the spring of the Ock was detected 60 hours later. And this shows the connection ultimately between the Danube and the Rhine rivers. So it was this water, and they still use not fluorescein, but rhodamines and radioactive things, but they still use these for groundwater tracing. Is this body of water connected to that one? You dump a dye in it. And so it's been popular. All these, you may think, wow, 10 kilograms, that's a lot to dump in a river. But even today, every year on St. Patrick's Day in Chicago, they add 40 pounds of fluorescein to the river. Well, now they started using a different dye. So I wanted to show this, okay? This is what I call the opposite of a single molecule experiment. Look at them, the powdered fluorescein flowing out the back of the bubble. Every year in Chicago,
Je pensais que ça allait être des zones, mais pédale quoi. C'est vraiment du vrai produit chimique.
Not exactly molecule. The whole river becomes green, and really they put it in the beer, and people are drinking this. And frankly, I always wondered if they put a UV hand lamp in the bathrooms, what this would look like. But that's another story for another workshop. So in 1887, Maurice Ceresol, who worked with Caro, who worked with von Baeyer, made rhodamines, and he made all the rhodamine dyes, and he calls it rhodamine because rhodo in Greek was rose and it was amine. But this guy made all these rhodamine dyes, rhodamine B, tetramethylrhodamine, rhodamine C, all from this guy. And there's a nice series of books by this guy, Cooks, by I think Carol Cooksey, Quirks of Nomenclature, and she talks about the naming of these things for those who are interested. And of course, Ehrlich in 1882 used uranin, which is the sodium salt of fluorescein, to track the secretion in the aqueous humor of the eye. And you've probably all had eye drops. That's fluorescein they're adding. Then they show the little blue laser, and you can say, wait a minute, that looks like 4 nanosecond lifetime when they do that. So the disodium salt was called uranin because it looked like uranium glass, the intense green from it. Already in 1887, NOAC published a book listing 660 compounds according to the color fluorescence. And that's the first molecular probes catalog. Mayer used the term fluorophore for the first time. And Heimstedt and Lehman independently developed the first fluorescent microscopes already. And Stanislav von Provosek in 1940 employed the fluorescent microscope to study dye binding in living cells. In fact, infectious agents of typhus is named after him and rickets. And this, right after he published that, he was studying typhoid and he died of the disease, but at least he published this. Albert Kuhn's labeled antibodies with fluorescein isocyanate. And I want to make the point, he used fluorescein isocyanate. Everything you use today, you use fluorescein isothiocyanate, which came in 1958, because it's much easier to synthesize. But he had the idea. And then, of course, we come to Gregorio Weber, who would talk more about at the end of this talk, who in 52 synthesized danazol chloride to attach the proteins. And he told me that he spent about 2 years to come up with a compound that was consistent with the instrumentation at the time. And the detectors they had was the eye. And he said, nobody believed these early phototubes would be useful. They were so noisy. And the eye was the way all of the detection you do. And then later, of course, we had Shimomura, who discovered the green fluorescent protein. And this is a nice picture. He's in his lab, in his basement, holding a sample GFP. This is what he isolated. It's not something he cloned or bought the plasmid and grew it. He isolated it from the jellyfish. Okay, and in fact, in that early work, he isolated, he had 30,000 jellyfish he had to cut up to get the GFP out of it. So if you had to do that today, you probably wouldn't do it. Now, one of the factors of interest in fluorescence was the commercial availability of probes. When I was a student, we had to build the instrument, synthesize the probe, and walk 5 miles through the snow to the lab every day. And it was uphill both directions, but that's another story. But it was Dick Haugland and Rosaria Haugland in their kitchen in Minnesota started molecular probes. And one of the important things they developed, the first thing was in Plano, Texas. They made Texas red, but then they moved to Oregon. And actually, when he sold the company, he got $325 million. So somebody made money with fluorescence. It was not Gregorio Weber, I can tell you, but they had the idea that developing Alexa dyes, because the problem, people started to do microscopy, but all the dyes available would photo bleach. Fluorescein photo bleaches in a moment. So they made a series of people use rhodamine because it was better, but they made the Alexa dyes, which were very photostable. They named them after their son, Alex, who was their son, so they called him Alexa. So they became the standard. And here's an example from their paper, Alexa versus fluorescein for photo bleaching. So that was important, that these people who developed these new fluorescent molecules. Now, of course, we have Luke Lavis and others, Genalia fluor dyes with these squaring things. And these are all the popular ones too, very photostable. We had Luke came to the Punta del Este meeting we had in January, and these are amazing. But this is a continuation of the original work by Weber, who would always design, he'd think of what experiment, what information does he want, and he would make the fluorescent probe, design it to get that information. Now let's talk about polarization, which we've heard a bit about in the course. And polarizers have been used a long time. The Vikings used a sunstone, which we think was calcite, as they went out to sail around and pillage and rob and kill and maim. They needed to know how to get there. And it was always overcast, but they'd use a sunstone. And if you rotate it, you could see in all directions the light was polarized by scattering, but not in the direction of the sun. So they'd locate the sun. So polarization was important. But it was Etienne Louis Malou in 1808 that observed that the windows, the reflection from the windows of the Luxembourg Palace would change when he'd rotate this crystal and look at them. And he's the one who coined the term polarized to describe this property of light. That comes from his paper, which he published in 1809. And he even discovered that when he holds two of them together and rotates one, that the intensity one is the cosine squared of the angle. So this all goes back to early 1800s. But it's David Brewster that studied the relationship between polarization of reflected light and refractive index. And he found that normal glass, an incident angle of 56 degrees, resulted in total reflection of one plane. This is called Brewster's angle. So you could make a polarizer from having a pile of plates, basically. And Weber, in his first instrument for his PhD, he used a pile of plates. And he showed it to me in the lab, and I'm sorry that somehow it's been lost. But it was just a pile of cover slips for slides, and you'd use that to polarize the light. So they're still reused. But it was Nicole that got the idea of joining two crystals of isolate spar together at the right angle, and then one plane of polarization would go through and the other would be reflected, and you usually put a black cylinder around it. Then there's others at the time, Glenn Thompson. Glenn Taylor is when you have an air gap, so you can go down in the UV. But the Henry Ford of polarizers, the man who brought it to the people, was Land, who in 1929 developed the sheet polarizer. So you could put crystals of iodoquinine sulfate and nitrocellulose, and when you stretch it, then it had the property of polarizing the light. And he made millions of dollars. And he started Land Camera and Kodak, but that's what brought them very cheap to everybody. Now let's talk more about polarization. I was talking about this paper to somebody yesterday, but this was a very important paper connecting polarization and energy transfer. This paper, in fact, was one of the main ones that get the interest in energy transfer. Gaviola, who we'll learn about later, and Pringsheim, Gaviola was an Argentinian working in Germany. They discovered, they used sodium fluorescein, urinin, and water-free glycerin. So it's very, very, very viscous. And they started off with like a milligram per mil. I can't imagine to this day how they dissolved it. But when you dilute that 1 to 4, the polarization was 0. This one, I think they probably dropped the test tube. 1 to 16, and they're using these, what we call millipole units. So this is 0.032 polarization. So very, very low. But as you dilute it and dilute it and dilute it, got something like you get 0.45. So they said, well, at very, very high concentrations, it's low polarization because you're getting energy transfer from one to another that's at a different angle. And that's what kicked off the interest in Brett. And now we get to Francis Perrin, the son of the famous Jean Perrin, and they had the first theories of energy transfer. In fact, he published obviously important papers, quantitative theory of fluorescence polarization, including what's considered to be the classic in 26. And that's what's known as the Perrin equation. Now people sometimes call it the Perrin-Weber equation. But it remained in the province of physicists for almost 2 decades until Weber began his thesis work in the mid-40s. But this was an amazingly interesting paper I have to tell you about. Look at the title, The Time Interval Between Absorption and Emission of Light in Fluorescence. This is in 1921 by the physicist R.W. Wood, who was a famous American physicist. At this time, they had no idea what was the fluorescent lifetime. No idea. Okay. So he had this beautiful experiment, which I love. And basically, he did this with his colleague from Wisconsin, Mendenhall. They made a pump that could pump a fluid of liquid out at 200 meters per second. And they did different dyes, anthracene, for example, and others. And at the end, they cleared a hole and they shined light in. And the idea was, let's excite right at the end of the nozzle. Let's see how far the stream is illuminated, right? If you know how fast it's going, you can get the lifetime. And unfortunately, they couldn't see anything, for which they deduced that the lifetime has to be shorter than 400 nanoseconds, which is still pretty good. They put an order of magnitude on it, you know? But then a few years later, and these guys actually very recently, 2013, they made one of these with a long-lived from terbium and europium, delayed fluorescence would get this, a microchannel chip. So this is microseconds, but they basically did Gaviola's experiment, and by measuring how this trails off, they would get the lifetime. So I said at the time, Enrico and I could try this in the physics building in Illinois. I said I would shoot rhodamine out at 10,000 meters per second and he would catch it in a bucket. But he never would let us do this experiment. So it's too bad. At any rate, the first measurement really came from Gaviola, the Argentinian who was working in Germany at the time, and he just described what he called ein fluorometer. It's important to note a fluorometer with an O, which is why Gregory Weber told me if it measures lifetime, it's a fluorometer. If it measures spectra, it's a fluorimeter with an I. That's the difference. And he didn't have a detector, but he used interference, and knowing the speed of light, he would calculate. And just to say how amazing his was, these are some of his professors: Frank, Hilbert, Planck, Einstein, Lisa Meitner. He had a pretty tough, you think you have a tough PhD committee. This guy really had one, you know. And this is from his paper. Sodium fluorescein, he got 4.5 nanoseconds. Rhodamine B, 2 nanoseconds, which is exactly right. So he did all that. And his machine was probably one of the most sophisticated scientific instruments in the world when he did it. Now, you'd think these fluorescent microscopes are all new, but this guy, Boneta, did it in 1959. And if you look at his paper, he took all these parts from a TV set and managed not to image, but to measure lifetimes using frequency domain. He was able to study fluorophores in some cells. So that's interesting that this was already in 59 anticipated. Now this sentence appeared in a 2006 book. More than 50 years ago, German scientist Forster discovered close proximity of two chromophores changes the spectral properties. And I hate that. Yes, he didn't discover this. He did important work. But the first work was probably Curio and Frank in 22. That if you have a mixture of mercury and thallium atomic vapors and you excite the mercury at 254, you could see emission from the thallium. And they knew that there had to be a transfer of energy. Then the famous Gaviola paper. Already in 25, Jean Perrin proposed a mechanism of transfer. Kalman in London got a quantum theory of transfer in 28. Francis Perrin did a quantum mechanical theory between molecules of the same species. And he had a qualitative discussion of spectral overlap. He didn't put it in quantitative, but Forster put that in quantitative, had the first quantitative theory. So, of course, he gets a lot of credit for that. Now, the first commercial spectropolarimeters arose because of the search for anti-malarial drugs. During World War II, the government issued a call to scientists and doctors to develop better treatments for malaria due to shortage of quinine again. Okay, so there were researchers at the National Institutes of Health in Washington trying to develop assays, but they didn't have good instruments. So Robert Bowman, who worked at the NIH and Laboratory of Technical Development, made a flexible instrument that you could move the excitation and emission monochrometers commercially. And those us old timers have seen and worked on these instruments. I won't ask everybody who's worked in them to raise their hand because it would be me and Enrico, and that's it. But at any rate, they were the commercial ones available. And here's a brochure from their 1956, cost $8,000. At that time, that's about $80,000 today. So it was a very sophisticated instrument. Now, fluorescence in the 20th century. Most of the basic principles were developed during the 20s and 30s. Gavriola did the lifetime. Quantum yield was stated for principles by Vavilov. Polarization of fluorescence first observed by Weigert and then quantified by Francis Perrin. Energy transfer, the Perrins and Forster. But until the second half, the use of fluorescence in biology was largely descriptive in nature, limited to the role in isolation, purification, quantification. Quantitative biological fluorescence began with the work of Gregorio Weber. So here he is and we say that as in all disciplines, development benefited from contributions from many individuals, but Gregorio Weber can be singled out for his far-reaching things. So let's do a little discussion of Gregorio Weber. So he was born in Buenos Aires on July 4th. To this day in the United States, we celebrate his birthday with fireworks. We have big celebrations. And there he is. I got this picture when he's 1 year old from Pancho Barrantes. He did an MD in Buenos Aires. He was a teaching assistant with Bernardo José. And Bernardo José, as I presume many of you know, was the first South American to get a Nobel Prize in physiology and medicine. And Weber or José suggested that Weber, continuing to get a PhD, go to Cambridge, England, and he got support from this British Council Fellowship, which was very difficult to get back then. His advisor was Malcolm Dixon. We'll talk about him later. He got his PhD in 47, fluorescence of riboflavin, diaphorase, and related substances, became an independent investigator at Cambridge. Then he joined the biochemistry department at Sheffield. In 1962, he went to the University of Illinois, where he stayed the rest of his life. And I was a student there, and Enrico was a postdoc there. But here is a picture of him when he was about that age, getting this fellowship. And he took, to go to England, it was during the war, 1943. And he had to go on a boat and had to go in a convoy. And he told me the story many times. And every time he told the story, it seemed to me there were more and more U-boat attacks on him. But so here he is going. I think if you look carefully, you might even see the U-boat. Yes, there's one. See, okay. But he made it to England. And then he entered St. John's College and he met Malcolm Dixon. And they talked about applying physical chemistry to the study of proteins. Now, at that time, Dixon was acknowledged as the world's preeminent physical biochemist. He's the guy who recorded the first absorption spectrum of cytochrome C. So you can see how Weber's interest in spectroscopy started because of this thing. And Dixon, somebody told him, oh, you should look at these papers by Perrin. Okay. So he said he knew little about it, but people knew that FAD and riboflavin were fluorescent. So Weber was given the task of sorting out this area. And he thought he'd work on it in a couple of years, and that went on forever. And of course, he was the first one to really working on FAD and NADH, which is now very popular. And that's his thesis, fluorescence of riboflavin. And here he is getting his thesis at St. John's College in Cambridge. And his first paper, actually, in 48, was this one, which was showing quenching of fluorescence and showing that this was a static, it's the first to demonstrate quenching can take place by formation of molecular complexes, what we would call static quenching. And to do that, he had to show that dynamic quenching changes the lifetime, static does not. But he didn't have a lifetime machine then, but he did it by polarization. And he's plotting the reciprocal of the polarization versus intensity over I0. And when it's dynamically quenched, the polarization goes up and up and up because 1 over P. But when it's static quenching, it doesn't change the lifetime until you get to very high concentrations. So this really delineated that we have static and dynamic mechanisms of quenching. Then he had his early work on FAD and NADH. This was the first one to show an internal complex of FAD. This is the first paper on NADH, basically. And he did energy transfer in NADH between the adenine and the nicotinamide. And in this paper, interestingly, in 1958, he calculated that the lifetime of NADH should be about 0.35 nanoseconds, which it is. It wasn't measured for another more than 10 years later by Weber, but that's pretty good. You just calculate from first principles what it ought to be. And here's, over the next 2 decades, he did lots of paper on NADH and FAD, and this anticipated all the work now on autofluorescence that happens. So the first direct measurements of NADH were done by Weber and his student Spencer, and they measured 0.38. And this is Gregorio Weber in the lab then, and that's Dick Spencer. That's actually Anna Jonas was a student, a postdoc. She's retired now, but she was very famous in apolipoproteins. But it was this machine that was the first one to use this cross-correlation principle that we'll talk about later. The final chapter, though, of his thesis is devoted to application of polarization measurements to determine viscosity of gels. And this is from his thesis of this determination of that's cytoplasm nowadays, protoplasm. Polarization appears convenient to determine this. And he distinguished between a microscopic and a macroscopic viscosity. That's because he told me he would make gels with fluorescein in them, and you could bounce the gels in your hand. The macroscopic viscosity was huge, but the polarization was 0 because fluorescein was in little pockets of water. But if you did rhodamine, it would bind to the fibers and the polarization would be very high. So that's when he conceived these ideas of micro and macro. And this anticipated the work he did 24 years later with Mayer Shinsky and others, using probes. They used Paralin and other ones to study the transition of lipids in micelles and membrane systems. And then Mayer Shinsky went back to Israel and developed diphenylhexatriene. So, and that became the most popular probe for many years until Lordan came along. So the use of probes in monomembrane systems has obviously become widespread and very important. What about designing probes? From 48 to 52, he did independent investigations, and that's where he started to design probes that let him study proteins, because intrinsic protein fluorescence from tryptophan and tyrosine had not yet been discovered, and they were discovered, of course, by Gregorio Weber. So he spent a lot of time and effort to make a probe that they could use, and after 2 years of efforts, he came up with benzoyl chloride, which is still used today, obviously. And his 52 papers were the theory and application. And I just wanted to flip through some pages. This is not a trivial thing like you put down the Perrin equation. If you go through that, it's really intense paper, okay? Because what he was trying to do, also at the end, he expresses his thanks to F. Perrin. I wish I had thought to ask him what did he talk about with Perrin. But he was trying to get generalized formulas for probes attached randomly to ellipsoids of revolution, not spherical particles. Remember, they had no X-ray structures then. So this is how you would get structural information. So he continued to advance the theory, in several papers. And in this paper, with husband and wife, Belford and Belford, physical chemist and mathematician, actually re-examined many treatments, including Weber's, and this presents the generally accepted equation for time dependence of polarization owing to rotational diffusion. So that was the final word on that. Now, in 1953, Hans Krebs recruited Weber to the biochemistry department at Sheffield. Of course, Krebs in 53 got the Nobel Prize for the Krebs cycle. Imagine discover a cycle named after you. That's amazing. But Weber continued to lay the foundations. And here's the Nobel Prize when there's Weber and there's Krebs sitting together. That's from the dinner celebrating the Nobel Prize in 53. So a lot of the work, he discovered, among other things, ANS. And this was the thing that you can demonstrate, and I think my lovely assistant is going to demonstrate this, that if you take ANS in water, it's got a weak fluorescence, but you add protein to it and it lights up. And if my lovely assistant could, unless Enrico wants to be my lovely assistant, no, he's not. But this is a good demonstration if you're teaching this stuff. So first you have a solution of AN.
Yeah. BSA.
That's just BSA, nothing.
The ANS, a little fluorescent.
It's a weak yellow fluorescent.
Look at now. Everything's ready.
You're supposed to go, ooh. Thank you, thank you. But the quantum yield increases about 200 times. It's really, but it's a beautiful demonstration in classes with undergraduates or high school. And it's still used today. More than 60 years after that report. When was that report? 1954. Well, more than 70 years after that report, they still use it in protein studies. Often it's an indicator of the molten globule state. So you always see this used even today. And but very importantly at Sheffield, with his postdoc, John Teal, they began to, Weber had predicted that the amino acids should fluoresce, and they discovered them. So this is the ultraviolet fluorescence of aromatic amino acids. Then, of course, they followed with the work on proteins, and figure 7 from this paper has been produced many, 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 many times. So this is from the paper. They showed the excitation spectrum of phenylalanine, tyrosine, tryptophan. And let me tell you, these are very hard to do today. They go down to below 210 nanometers, really difficult. So if you ever tried this, you'd appreciate how careful and how much work this was. And this is the plot that's reproduced so many times, phenylalanine, tyrosine, and tryptophan. Now, a few years ago, I was working with NASA. I got on the committee somehow where they want to send a probe to Europa, the moon of Jupiter, where they wanted to send me, but they said I was too heavy, so I couldn't go. But at any rate, in the project describing this, they want to look at other things, including search for life. This is one of their flyers, but I managed to get this inserted in the life detection, and I think Gregorio Weber would be very happy to know that his figure from that paper is now used by NASA. So that's really spectacular. So any rate, what about other probes? Well, he designed BIS-ANS, and I won't go into the story, but it's an amazing story how he discovered that. And of course, IEDANS, which is the first sulfhydroreactive probe. So he has an alkyl halide. He wanted a probe that would specifically attack cysteines, and that was the first one. And pyrobutyric acid, the first long lifetime probe. This was more than 100 nanoseconds. And of course, the famous DAN series of probes. Prodan, Danca, which he used for studying heme pockets, and Lordan. And there's a picture, again, Lionel showed this. Lordan or Prodan, it looks the same, and -80 in glycerol, and +60, you see this beautiful solvent relaxation, or glycerol is relaxing, that's the solvent. But it's a wonderful probe. And again, he designed these to have a large dipole moment. As he told me, I was there when he was doing it. So this would stabilize a positive charge, this would stabilize the partial negative. So he knew when he had a large dipole moment, it would be very sensitive to the polarity of the environment. And it was all made in this lab with his technician, Fay Ferris. And if you were in Weber's lab, as Enrico knows this, you were scared to death to walk into this lab. Again, this is before environmental protection agencies, and there were solutions and things. It looked like an alchemist laboratory. All those probes came from this laboratory, incredibly. So phase fluorometry in the 50s, he started to think about lifetime, and of course, maybe he was inspired by the work of Gaviola, a fellow Argentinian. And while at Illinois, they with Dick Spencer constructed a versatile frequency domain measurement, frequency domain instrument, and they used this technique of cross correlation, which is key to modern fluorometry, still used university, where very simply, in simplistic terms, you modulate, let's say, the exciting light at, let's say, 10 megahertz plus 400 hertz, and you modulate the detector, the diodes at 400 at 100 megahertz. So there's a 100 or 400 hertz difference between them. And so at the end, you're looking only at that signal at low frequencies. But it turns out to be the method that's generally used. So that led to multi-frequency when Enrico came as a postdoc, and he worked at the suggestion of Weber there on the campus there on a development of a phase and modulation fluorometer with variable frequencies. And Enrico did it. He went back to Rome, and then he came back in 78 as assistant professor. By that time, he'd already finished the true multi-frequency instrument using a Paco cell to modulate, thus completing Weber's vision. And here we see Gaviola's machine, Spencer and Weber machine with his Dubai Sears tank, Enrico's machine, and now you have any number of microscopes that do this. It all started through this early work. Now, in that original paper, well, I should say, Weber had a paper where the question was, if I give you the tau phase and the tau modulation at two frequencies, can you analytically tell me what the lifetimes are? And it was a very difficult thing. And he did this. And in fact, he said he used the classical de Prodi method. Well, it's much more interesting than that. He developed a mathematical method, his own, he developed. And then he said his friends at the university, mathematicians, said they think they've seen it. And I went with Weber to the math library in Illinois, where he found this 1795 paper by de Prodi, where he describes this. And in the paper, he said he used the method of de Prodi. And I said, well, you developed it yourself. Why don't you just say you developed it? He says, no, de Prodi did it first, so he must get the credit. So that is scholarship. Okay, but in here, he put down these equations for GNS in frequency domain and in time domain. And these are the basic terms that are used in the phasor plots. By now, you know that. And this, of course, is Enrico's vision of applying this to FLIM imaging. And you've heard all about this by now. And what awards did Weber get? Well, a lot. This was a big one in the States. But he was, those of you that go to the Biophysical Society know that they always have a national lecturer. Well, he was the first one when they started in '69 to give the big lecture to the whole society. And he won other ones, Argentina, US National Academy of Science. And I'll come back to this. This was his favorite, he said, and some other ones. But he liked the Rumford Premium, established in 1839, one of the oldest scientific prizes in the US, and recognizes contributions to the fields of heat and light broadly interpreted. So it was started by a bequest from Benjamin Thompson around Comfort in 1796. And Weber's getting it, and the other two guys are Mills and Yang. Yang got the Nobel Prize for his work on gravitational gauge theories, whatever. But Weber liked it because he said the other people who got it over the years include Gibbs, Edison, Wood, Michelson, Bridgman, Compton, Land, Enrico Fermi, Onsager, Frank. He said that's a pretty good list to be included in, he found. So, and more recently in '85, the American Chemical Society gave an award for chemistry of biological processes. The first one to get it was Weber for his work on proteins, not because of fluorescence, but I could give a complete lecture for Weber's work on proteins, but this is a fluorescence meeting, so we talked that. But he was the first one to get that too. Now we've had these international symposium honoring Weber, and Enrico and I organized most of them. And the first one was Bocca di Magra, Italy, and here we are. There's Weber being hidden by Marisa. There's Enrico. I'm somewhere in there. But if you that's Jim Longworth, who was Gregorio Weber's first graduate student. At any rate, a lot of these are the old time fluorescence field. Well, there's Weber, there's Enrico, there's me. But then we had them after that in Frascati, then we switched to Hawaii. Maui, Kauai, 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 Kauai. You say, why not Kauai still? Because it got too expensive. And then Buzios, here's the partial group meeting in Kauai. And this was Buzios in 2017. And of course, then we had Punta del Este in January. So I don't think I'm up to date on that. But I wanted to stress that these meetings, even though they're in a fun place, are known for their total focus on rigorous science. And here's Enrico demonstrating fluctuations, and he took it very seriously. There's a certain rhythm. And to this day, I remember, this is really true. I was sitting in the audience with Enrico, with Gregorio Weber at one of these, and they had the Tahitian dancers going, and the hips are going. And Weber said to me, David, the one on the right has a much higher duty cycle than the other ones. And I thought, what a scientific way to put it. Because I was thinking something else, but it's another story. And in Buzios, the last meeting was actually Punta del Este. But again, here's Enrico demonstrating diffusion and particle tracking. So we really pay attention to this stuff. So that's right, the 11th was here. And I should say the next one is now scheduled for 2025 in Genoa, Italy. So we hope to see you all in Genoa. But you can find a lot about Gregorio Weber on the LFD webpage. They have a lot of information. And I edited this book that has a lot of interesting stories, like Weber's Roots in Argentina by Barantes and others. And anybody that wants this book, send me an email. I'll send you a PDF. Because it turns out the publishers sell this for like $350. I couldn't believe it, which is a little ridiculous. So I'll give it to you. And there's more tributes on the LFD page. And I have a page where, we talk about it. And one of his undergraduates, David Lloyd at Wales, started this web page, which is still active, where a lot of the early people wrote memories about him. And it's interesting to see. It's mainly the early people. And there was this great one by Fred Sanger. I hope the young people know Sanger. He got 2 Nobel Prizes, one for sequencing proteins and another one for sequencing DNA. And as Weber told me, they worked down the bench from each other. And he said, I do not feel able to comment on Gregorio's scientific work. It was in another field. I do believe his contribution was considerably more than appeared in print. During the time we were both working in the Cambridge Biochemical Lab, he would frequently come over to my bench to see what I was doing, discuss my work, and make useful suggestions. I found this stimulating and often helpful. because Gregorio had a considerable wider knowledge of science than I did. But it's hard to describe to you people who never met him what a towering intellect this guy was and what a great human being. And I'll end with this. This is an actual conversation. Believe it or not, that's me. Okay. This is an actual conversation, really, that took place between me and Weber in Hawaii when he's visiting me once. And he said, you know, David, when I was much younger, an older colleague said to me, Gregorio, when you pass the age of 60, you'll begin to notice that your students have more ideas than you and better ideas than you. And I said, gee, really? And he looked at me for a very, very long time. And then he said, I have not found this to be the case. And I thought to myself, well, now that Enrico and I have passed this age, what if we were included in that conversation now? And he said, how about you, Enrico? And I imagined what Enrico would say in their dreams. And if he turned to me, I'd probably say, huh? But that's it. But I hope I give you a flavor of the history of fluorescence and a feeling for how wonderful Gregorio Weber was. So that's it. Thank you.